So let us talk about some of the future tsunami scenarios in Cascadia. When we think of Cascadia, the first mental image that we have in our mind is of this huge rupture that's going to break the entire plane interface in the US West Coast. And it's going to create this monstrous tsunami that I'm showing a video of here. The jury is still out on the shape and size of the rupture and what the magnitude of that would be. But I think an important question is how big of a tsunami is it going to make? And does the worst case tsunami scenario necessarily correspond to the worst case rupture scenario? And this is the question I'm trying to answer in this talk. Now, before I start all of that, I'm going to provide a really quick background on how we do things in the tsunami business. So as a result of the earthquake, we think this is the way we do this. The ocean floor gets deformed, here shown in brown, and the formation itself is sort of transferred to the surface of the ocean. And that's going to create a gravitationally unstable system of bumps and troughs on the surface that's going to move around as a result of the force of gravity, and we call that a tsunami. The speed of tsunamis are given with this simple equation, square root of GH, G being the acceleration due to gravity, and H being the depth of the ocean. So what this tells me that if I have these two pieces of information, a good map of the ocean floor giving me depth and a good understanding of the surface, I'm in business. And these are called initial condition in the tsunami business. We usually have a good understanding of the ocean depth because we have bathymetry maps. All we need to do is come up with a good understanding of the shape and size of the source. Now, moving on to Cascadia, from the advent of plate tectonics, we have had this notion of this huge subduction zone on the US West Coast. But it was not like any other subduction zone because it was not making any big earthquake in its history. And it was a big enigma until Tom Heaton and Park Snavely in 1985 published this paper in BSSA, and they argued that they'd inferred from Indian traditions the existence of these events in the past. A couple of years later, Brian Atwater published this now famous paper presenting evidence of the existence of these rupture in the past from geological data. And he finishes the paper with a cautious note saying that we don't really know how big of an earthquake it will be. And then later on, it was followed with a huge number of papers, and Kenji Sataki in Japan and his team, they sort of discovered this orphan tsunami in the year 1700, which didn't have an apparent earthquake as parent. So they followed up this study with a number of other studies in collaboration with other teams and concluded that it was most likely an earthquake in Cascadia, probably a magnitude upper 8 to magnitude 9 earthquake with a distribution, with some distribution candidates as for a slip. Now, this is one data point that we have. What may happen in the future is the big question. And if you just do a little Google search, and this is what I get within my filter bubble from a 1700 Cascadia earthquake, and it has an ominous picture here on the right saying that, well, it doesn't necessarily explicitly saying that, but implying that this is probably something that happens in the future. And this is called the sort of the worst case scenario in ace in a hole. Now, if plate tectonic has taught us anything over the past 60 years, is that, well, this is not necessarily the one scenario. We can get a variety of magnitudes and locations in subduction zones, and this was pioneered with the work of Ando in 1975. He basically divided the Nankai Trough into a number of chunks and argued that, this could either break in one earthquakes or a number of them over time. And of course, this distribution follows some statistics. And if you know the statistics and have some insight with plate tectonics, you can actually create a large number of fake earthquakes in Cascadia, as Diego Melgar's group have done, and produce a large number of tsunami simulations for that area. And this is exactly what various groups have been doing over time. But as we all know, the bane of existence of this kind of a study is this curve, which is the total cost against mitigation level. And this red curve gives you the calculated model. Now, you can play around with all kinds of mitigation scenario, but at the end of the day, you have to converge. I mean, it's best if you could converge on this optimum scenario where you can spend the least and get the most out of your model. And this is what you need some physical sense to do. And in order to just, to answer the question whether or not, we are under mitigating or over mitigating with each of these scenarios, depends on the number of on tsunami simulations. So let's simulate some tsunamis here. So this is remember, we need some initial condition as a form of ocean floor deformation from an earthquake. And this is what we predict from locking models. We basically tell you that I can measure deformation on land and can sort of, with some tricks, extrapolate it offshore and say, well, over time, we know that this amount of strain has been accumulated. And so this is going to be what's going to happen offshore as a result of a magnitude 9.2 earthquake. So this is based, in other words, this is slip potential. And so I take this slip field from Gina Schmalz's work in 2014 and try to downscale it using earthquake scaling laws to get smaller slips down to very small earthquakes. And from that, I can simulate ruptures. I can say, well, I start from the north, for example, here in magnitude 8 scenario, and I rupture southward until I saturate. And this means that I'm pulling from these slip values for a magnitude 8 scenario. And this is just an example here for magnitude 9. I start from this little dot here in the north and propagate the rupture in the corresponding slip field until I saturate the magnitude 9 level. And then I can move around the rupture, the epicenter, to get other earthquake scenarios for magnitude 9. And I can do this for all kinds of magnitude scenarios. And this is what I get. Remember, I applied those initial conditions, deformations, to my tsunami simulation codes, and here is what I get. So here, the bottom panel in these two figures is basically the exact same thing in the previous slides, just flipped it on its side. You have this mesh as the rupture mesh, and then these both panels on top, I have these black curves which correspond to the tsunami profile along the coastline of Cascadia and the U.S. West Coast. And the rest of the curves are other scenarios color-coded according to the latitude of the epicenter. So for example, the blue curves here correspond to the blue parts of the rupture, whereas the red curves correspond to the southern chunks. And same thing with the magnitude 9. Now, there are three key points I'd like you to take away from this slide. One is that, well, central segments of the subduction zone make wider spans of high amplitude, which means that if I put the rupture in the north, it's going to create a smaller rupture, but it's going to be more local, a large rupture, but it's going to be more localized. And I move it to the south, I'm creating comparable tsunami amplitudes, but it's more widespread. And this boils down to the second point in question here. For magnitude 9, if I put the source in the north, I'm already saturating the magnitude 9.2 scenario. And if I move it southway, I'm actually getting about 90%, more than 90% of tsunami amplitudes of in the entire span of the coastline. So upper magnitude 8.7, 8.8, 8.9 seem to be actually good representations of magnitude 9.2. And finally, the maximum tsunami amplitudes occur somewhere here in the middle of middle and Oregon State. It's because we think it's mostly due to the concave shape of coastline, which focuses tsunami edge waves somewhere in the middle. Now, what about the effective rupture model? So remember that I mentioned that we use Gina's model here, which a special form of it, which has deformation right off the trench. What if we change the rupture model? So here, to study this, here we have George Priest's model, a simplified version of it. And here we have a dynamic rupture that's sort of derived from a locking model. And each step I can simulate the tsunami, and this is what I get. This is the map of tsunami amplitudes all across all of these models. And as you can see, as we move away from the coastline, in other words, in the far field, these models are very different. But what about the near field? And they seem to be very similar. And in fact, if you look at the tsunami amplitude profile, this is what you get. Here, this is remarkable. They're strikingly similar because the blue curve corresponds to locking model here, and the red curve in each case correspond to the alternative scenario, rupture scenario. And the important pattern is that they have very striking correlation. In fact, they have a correlation more than 0.9 in each scenario. The difference is the absolute amplitude of the run-up or the coastal amplitude, which could be attributed to either different scaling laws that you could use or the lack of complex bathymetry. And so, in other words, as long as you're not ignoring a large patch of rupture, a patch of slip, as we are here, for example, the difference between these two being this huge cluster in the south, you're good. The choice of rupture model doesn't really matter in the near field. And this is, I think, a very important understanding of the limit that you can put on your tsunami scenario. So the bottom line is that for Cascadia, if you recall this curve that I showed you before, we can put some labels on this. Magnitude 7.5 is probably, and plus some other things, are going to be at both ends of this. And magnitude 9.2 is very over mitigation. And we put the upper magnitude 8 in the middle. It's probably the sweet spot that you want to plan your mitigations with. Remember, we can go ahead and make these huge structures along the coastline, but at the end of the day, these are costly, because you can do a kind of a quick and dirty calculation and sort of figure out that the cost of building this kind of coastal structure in billions of dollars is going to be exponentially increasing as you raise the magnitude threshold. So we think if you put the cap here in somewhere 8.7, 8.8, you're good even in this regard. And there are all kinds of things that you can do in between. You can go ahead and do some lectures. You can do you can educate coastal communities. You can work on GNSS stuff, which are actually perfect in terms of tsunami warning. You can expand on the existing DART system, or you can use innovative and very promising systems such as this, smart cables. But the bottom line is that it's all a question of what you choose, and it's also a question of what the community needs in terms of either short or long planning. So, for example, you can do science assessment, reassessment, then you can feed in your models what your output to the economist, and they can calculate these curves. And then there is the question of how to mitigate, how to use this information to warn the public. And remember, you cannot really make this a structure all across the coastline. You need to take many, many other things into consideration. And at the end of the day, it's the combination of all of this with a bit of insight from further insight from science that results in policy. Thank you.